Welcome everyone to this explainer. Let's jump right in, because today we're tackling a topic that might seem perfectly clear on the surface, literally. But underneath, it is a high-stakes world of life safety engineering. We're talking about glass railings. Specifically, we're diving into the critical differences between laminated fully tempered, or LFT, laminated heat strengthened, LHS, and the showdown between PVB and SGP glass interlayers. You see, when a glass balcony looks out over a massive drop, the engineering behind that transparent barrier is literally the only thing standing between a beautiful view and a fatal disaster. We're going to break down exactly how these systems work, why they fail, and how modern engineering keeps us safe. So here's our game plan for today. First, we'll look at the post-breakage safety problem. Second, global building code rules. Third, we'll decode glass manufacturing processes. Fourth, PVB versus SGP interlayers. And finally, number 5, specifying your railing project. All right, Section 1, the post-breakage safety problem. For decades, the entire industry was completely obsessed with how strong glass is before it breaks. But I want to pose a really critical question to you right now. What happens when the glass actually breaks? It's a question that challenges a very common and honestly very dangerous assumption. The assumption that strong glass is automatically safe glass. Because as we're about to see, immense strength can sometimes lead to the most catastrophic failures. Think about this stark reality here. If you take a standard 10mm monolithic fully tempered glass panel, the kind we used to see absolutely everywhere, and it breaks, well, all that stored elastic energy releases at once. It shatters into tiny granules that just fall away in seconds. In an instant, you have zero barrier function. A drop-off is completely exposed. Now compare that to laminated glass. When laminated glass breaks, an engineered chemical inner layer physically bonds the broken fragments together. It might sag, it might crack, but it stays in the frame. It retains a residual barrier, and that is absolutely vital for life safety. Now, you might be wondering, why would a super strong glass panel break in the first place if nothing hits it? Well, enter nickel sulfide, or NIS inclusions. These are microscopic manufacturing defects hidden deep within the glass. Industry data estimates that roughly 1 in 3,000 to 4,000 panels actually contains this defect. And over time, these tiny inclusions expand, and they can cause spontaneous, catastrophic glass breakage without any external impact whatsoever. Zero warning. That kind of sudden monolithic failure is just an unacceptable risk when people's lives are on the line. Which brings us to Section 2, Global Building Code Rules. Code authorities worldwide haven't just been sitting on their hands about this. They have actively reacted. The prohibition of monolithic tempered glass isn't just some engineering theory anymore. It is strict, undeniable law across major global jurisdictions. In the US, the IBC 2021 code makes laminated glass completely mandatory for all guard infills. Canada's NBC requires it for exterior balconies above the first floor. Australia's AS 1288 dictates it for critical balustrades, and Europe's EN 2543 demands rigorous structural safety configurations. So the global consensus is completely unified here. Monolithic glass and barriers is out. Section 3, Decoding glass manufacturing processes. To really understand why these specific glass types behave the way they do in service, we have to look at how they're made. To understand glass, you have to understand its thermal history. The tempering process starts by taking float glass and heating it up to roughly 620 degrees Celsius. Then it's rapidly cooled, a process called quenching, using high-velocity air jets. Now, the outer surface of the glass solidifies and contracts first, but the liquid interior cools much slower, and as it tries to contract against that already rigid outer surface, it creates an immense, permanent state of internal stress. And this creates what we call surface compression. The surface is locked in compression, and the core is locked in tension. Any applied load has to overcome that massive surface compression before the glass fails. This incredible engineering is exactly what makes tempered glass 4 to 5 times stronger than standard annealed glass. But it is a double-edged sword. That immense stored elastic energy guarantees total explosive destruction into tiny granules when it finally yields. This brings us to a really fascinating trade-off: fully tempered glass versus heat-strengthened glass. Fully tempered boasts a massive surface compression of at least 69 megapascals. But as we just learned, when it goes, it breaks into tiny granules. Heat-strengthened glass, on the other hand, is cooled much slower. It has a lower compression between 24 and 52 megapascals. Now, why on earth would we want weaker glass? Well, because when heat-strengthened glass breaks, the lower stored stress means it breaks into much larger fragments. In a laminated assembly creating laminated heat-strengthened, or LHS glass, those larger fragments give the chemical inner layer so much more surface area to grip onto, providing far better edge stability and structural integrity after a break. Moving right along to Section 4, PVB versus SGP inner layers. We know we need laminated glass, for sure, but now we have to choose the engineered chemical material that actually holds the broken fragments together. In one corner, we have PVB, or polyvinyl butyryl. This is the highly reliable baseline standard for most architectural glass. If the glass breaks, PVB holds it together, but the panel is going to sag under its own weight like a heavy blanket. It also softens at high temperatures. In the other corner, we have SGP, or Sentry Glass Plus. This is a premium ionoplast inner layer. When SGP glass breaks, it retains incredible lateral stiffness, meaning it stays rigidly upright. And it is highly moisture resistant, which prevents that ugly, milky edge discoloration you sometimes see. So the crucial point boils down to this number, 100. SGP is roughly 100 times stiffer than PVB in a broken state. And that isn't just a minor upgrade, folks. That is a massive structural leap in residual life safety. If someone falls against a broken panel, an SGP laminate actually has the rigidity to potentially stop them from going over the edge. When you put laminated, fully tempered glass with both inner layers head-to-head, you see some really distinct differences. While both beautifully meet the base IBC 2021 code requirements, SGP dramatically outperforms PVB in structural retention. When broken, PVB offers a limited barrier because it just sags, while SGP offers significant stiffness. And for wet environments, like pools or coasts, SGP offers good edge stability compared to PVB's fair rating. Finally, Section 5, specifying your railing project. Let's transform all this vital theoretical data into a practical toolkit for your work. Upgrading from PVB to the stiffer SGP inner layer is an absolute necessity in a few high-stakes scenarios. You need SGP if you're designing a frameless guard with no top rail to pass those strict safety tests. You need it for exterior balconies above the third floor, out in high wind zones, around pools or coastal areas where salt and moisture degrade the edges, and absolutely anywhere you have overhead glazing or structural glass floors. To give you a tangible starting point, consider these baseline thickness metrics drawn directly from industry practice. For standard residential guards with 800 to 1,000 millimeter post spacing, you're generally looking at starting around 10 millimeters of LFT glass. Commercial projects move up to 12 millimeters, and commercial wide spans push up to 15 millimeters or more. But remember, these are just starting guidelines. You absolutely must always run your site-specific engineering calculations. Let's pull it all together with a final sequential decision checklist for architects and specifiers. Step 1. Confirm your local code compliance and safety baseline. Step 2. Select your glass and inner layer combination, LFT or LHS, paired with either PVB or SGP. Step 3. Get a structural engineer to rigorously verify your thickness based on wind and load. And Step 4. Demand quality assurance, requesting heat-soaked glass if spontaneous nickel sulfide breakage is a major concern for the project. I want to leave you with this final provocative thought. If a frameless panel on a 30th floor balcony shatters tomorrow from a hidden microscopic defect, what is standing between the occupant and the edge? Well, if it's monolithic glass, the terrifying answer is nothing. But if it's properly specified laminated safety glass, the answer is brilliant, invisible engineering. Keep that reality front and center in your design philosophy. Thank you so much for joining me for this explainer, and stay curious.